will now cover section 2.2, and we will start with histograms. Histograms are used to represent large numerical data sets. The vertical axis is either the frequency or the relative frequency or the proportion of observational units with a particular numerical data set value. And the horizontal axis will be the variable that is a numerical variable. Regardless of the label of the vertical axis, the shape of the histogram has to be the same in all cases, and we saw an example of that in Project 2. Histograms provide information about the shape, the center, and the spread of the data, which is the main concepts that we will cover in this chapter in Unit 2, where we will do statistical summaries of data. So histograms have the same properties, have the following properties. The rectangles are centered over the interval they represent or the value they represent. The rectangles have the same width. Their height is equal to the frequency or the relative frequency for this particular data value or set of data values, and they are attached to each other. To construct the histogram from scratch without any additional information, we have to decide on how many bars or interval or classes we will have. They are called classes when you see them on a table usually. The bars will be the histogram rectangles, but in Excel they are called bins. So bins will correspond to the interval of values for the data. Most often, and for clarity, we aim for between 5 and 15 classes. And then we choose a starting point, usually less than the minimum data value. And we go about to cover all the data values that we have based on the number of intervals we have selected. Now, a convenient starting point for the first interval of a histogram is to take the lowest data value and carry it down one more decimal place than the accuracy of the data value with the most decimal places. And we will see some examples very soon. So actually the starting point is not a value that corresponds to one of the data values that we have. Because what this thing says is that if you have a data value that has the most decimal places, you will do one more decimal place of accuracy, which means none of your data values is that accurate. So the starting point and obviously the ending point are not data values in your set. The ending point will be the largest data value and going a little up, so a little larger than that. How much larger? One more decimal place than the accuracy of the data value with the most decimal places. So therefore, to find the width of every one of your bins, what you will do is you will find this imaginary starting point that is less than your smallest data value and the ending point that is larger than your largest data value. You will subtract them and then you will divide by the number of classes, and that will be the width of every class or the width of every bin, like Excel wants it to call it. So the width is the difference between the ending point minus the starting point divided by the number of classes. And the rest of our notes have a little bit of math here just for you to demonstrate how to find this starting point and ending point. So what we do is we halve the place value of the most accuracy that we have. So if our data goes by tens, we will have a 10. Half of 10 is 5 units, and that will be 5 will be the accuracy that we will require for our starting and our ending point. And then if our data values go by hundreds, we will halve 100, and that will be 50. If our data value go by thousands, then we will halve the 1,000 to get 500 and so on. So if our data is in millions, let's say millions of dollars of debt, then we will halve the million to get an accuracy to 500,000. And if our data are decimals, and let's say they are rounded to the nearest tenth, then we will halve the tenth. If they are rounded to the nearest unit, we will halve the unit. So our accuracy for the starting and the ending point will be at a 0.5. But if they are in the tenth, we will halve a tenth. And then our accuracy for the starting and ending point will be at 0.05. And if our data is accurate to the thousandth, we will have a thousandth. Now, there is a pattern to that. So how does it work? When you halve a place value, the accuracy now becomes one additional place value. So one place value lower, I should say, which means to the right. So 0.00, and this one that was actually a 10 will cut in half, and it will become a 0.5. So if you think about it, if you had your data to the 10, they were going by tens, then you would have that 10, and here will be your accuracy. Half of 10 will be 5. But if it was 100, then this 10 will be halved, and your accuracy will be at 50s. Or if it was 1,000, then this 10 would be halved, and your accuracy will be at 500. So same thing at decimals. When you are at 0.1, you are looking at this 10, and then when you halve it, this will become a 5, but now you are one decimal place to the right with your accuracy of 0.05. So that's how we find how to start or how to end. Now, what do we do with this? When we find the accuracy that we want to be able to have the starting and the ending point, we take that accuracy and we subtract it from the smallest value and we add it to the largest value. That's how we will find the starting point that is smaller than our minimum value and the ending point that is larger than our largest value. And it also cannot be one of our data values. So we want to go in accuracy further than what our data is, so that we know that we will never hit a data value that we have. Examples. If the value with the most decimal places is 6.1, then this has accuracy to the nearest tenth. I will halve that accuracy, the 0.1, and it will be 500ths. And then if the smallest value happens to be 6.1, I will subtract the 0.05 from 6.1, and I will start at 6.05. 6.05 has more precision than any of our data values. Also, when the starting point and other boundaries are carried to one additional decimal place, no data value will ever fall on a boundary. Why do we care? If we are looking at ages and we say from 1 to 13 and from 13 to 26, somebody who is 13, where are they classified? Are they classified in the 1 to 13 group, or are they classified in the 13 to 26 group? So in reality, we don't want our borders to ever fall on actual data values. That's why we proceed with greatest accuracy. If the value with the most decimal places is 2.23, it has accuracy to the nearest hundredth. Half of 100 is 0.005. Remember that for the hundredth, I'm going to go one more decimal place to the right, which has lower accuracy, or higher accuracy, I should say. It has a smaller place value. and that's how I'm going to find it. And then this will be my accuracy, and it will be subtracted from the minimum data value. If the minimum data value is 1.5, then my starting point will be 1.5 minus 0.005, and that will equal to 1.495 will be my lowest data value. If the value of my data with the most decimal places is 3.234, this is accuracy to the thousandth. A thousandth as a decimal number is written as 0.001. And the lowest value will be, let's say, 1.0. Then 1.0 minus half of that accuracy. Half of 1,000th will be 0.0005. So 5 10,000ths. 1.0 minus 5 10,000ths is 0.9995. If all the data happen to be integers and the smallest value is 2, we have accuracy to the unit. Then the convenient starting point will be the smallest value, 2, minus half of the most accuracy we have. Half of 1 is 0.5, and therefore we will start at 1.5. So, this is some logistics. Usually we use technology, and technology that does statistics better than Excel does. And these are already embedded and coded into our technology, so this is nothing that we worry about. Usually we just have the data, and then we give the data to our technology, and the technology generates the histogram. The one thing that we do have to tell Excel, as well as any other statistical software, is how many bins do we want to have. And then all of this math is done in the background, and we don't have to worry about it. Now, the reason we are mentioning it is because you do want to be able to see how a graph is interpreted. And before we go to the next example in our notes, which we also will do in Excel, I want to go at our homework. And in Unit 2, question 13 in the homework, 2.1-7. So in homework for Unit 2, question 13 has this graph. And the story is that during one shift, the express lane clerk recorded how many times customers violated the sign. The sign says 10 items or less for this lane, which is the express lane. So a person violates this sign if they come to the cashier in the express lane with more than 10 items. So 10 items or less means you can go there if you have purchased 1, 2, 3, 4, etc. up to 10 items. But if you have purchased 11 items, or you want to purchase 11 items, and you go to the express lane, then you are violating the 10 items or less rule by 1 item. So in particular, this express lane clerk recorded how many items over the limit each violator placed on the conveyor belt. So again, if you go with 11 items, then you are 1 item over the limit. If you go with 12 items, then you are 2 items over the limit, etc. And the data is summarized in the histogram below, where 7 or more items is listed as a 7. So if you go with 17, with 18, with 19, with 20, we just count you as just being at the 7. So this last class is tricky. Now, the reason I want to mention this is because if you pay attention to the graph, and I have copied it here, the data in the bottom which is number of items over 10 over here, these are decimals. And there is no way that any customer comes to the express checkout with 1.5 items extra. Your items are discrete numerical data. They are counting numbers. So what does a box, let's say here, what does this box that has a base between 3.5 and 4.5, what does this box indicate? So this is exactly what we are talking about with the accuracy. So when you are counting items, the accuracy of your data is to the nearest unit, because when you are counting, you're counting whole numbers. 1, 2, 3, 4, 5, 6. They are called counting numbers. So this histogram was generated by dividing this unit into half so that we can have half units. So when we are in the first interval, and the first interval is from 0.5 to 1.5, this is because the number 1 is there. So someone went with 11 items and violated the sign by 1. And then the next group, 1.5 to 2.5, has violated the 10 items or less by 2. So when you are in this middle bar that is from 3.5 to 4.5, the actual value of number of items over 10 is 4. So when they are asking you, what is the frequency? What is the frequency means how many times? The time limit, the limit was exceeded by more than 4 items. More than 4 items will be 5, 6, 7 or more. They are asking you how many times somebody went there with 15, 16, 17, 18 or more items in the express lane. And that, let's erase our mess here. All right, so the question is where is 5 and where is 6 and where is 7? So 5 will be between 4.5 and 5.5, and 6 will be between 5.5 and 6.5, and 7 or more was recorded as a 7 between 6.5 and 7.5. So the rectangles in question are the last 3 rectangles that we will be taking into consideration. So here my answer should be the frequency of this tallest rectangle, and remember the height of the rectangle is the frequency. So this looks like it is 13 because the horizontal line limits are going up by 2. And then these guys look like they hit at the 6 and at the 6. So my answer here will be 13 plus 6 plus 6 or 25. That will be my answer for this. So make sure you understand how to read histograms that use accuracy beyond that of the data. Now let's go back to our notes to try to do a histogram by hand, and then we will do it in Excel and see how it works in Excel. So the following data are the heights to the nearest half inch of 100 male semi-professional soccer players. So these are heights of male semi-professional soccer players. And they are measured in inches to the nearest half inch. So some of them are decimals. And therefore the horizontal axis, this is my variable, will be heights in inches. And the vertical axis per instructions that ask us to construct a relative frequency histogram will be to do percent of athletes. So the question is, what will be the starting point? What will be the ending point for our histogram? And the directions are that, let's suppose we choose 8 bars. So the number of bins will be 8. They are asking us what is the width of every bar and how are we going. You will see that we will get something very weird as a value, and we will round it here. So if you remember, since the biggest accuracy is at a 0.5, that is the nearest tenth. The nearest tenth is 0.1 accuracy of our data. So we will take this accuracy and we will divide it by 2, which will give us 0.05. And then to find the starting point and the ending point, we will subtract 0.05 from the smallest value, and we will add 0.05 to the largest value, and these will be our starting and ending points. Now the smallest value, this data is ordered from smallest to largest, is 60. I see it here. So my starting point will be 60 minus 0.05, so 59.95 will be my starting point. And the ending point, my highest is 74. It will be 74 plus 0.05 will be 74.05. None of these values is a data value in my data set. To find the width of every bar, I will subtract the two values, 74.05 minus 59.95, and I will divide by the number of bins, by the number of classes. I want to have 8 bars per instructions. And when I do this math, it comes out to be 1.7625, which doesn't make sense in terms of heights. So we will round up to 2. And then if we start at 59.95 and I add only 2's, I will always have 2 decimal digits of accuracy. So I will never hit a data value at a border between 2 classes. So when I am ready to do it by hand or with very much better software than Excel, I will start here with 59.95, and the next one will be 61.95, and the next one will be 63.95, and the next one will be 65.95, and 67.95, 69.95, 71.95, 73.95, and unfortunately 75.95. So I have gone a little farther than 74. And I will need to know how many values are between 59.95 and 61.95. And these are 60, 60.5, 61, 61, 61.5. So these guys here will be in my first bin. So 5 of them. So if this was the number of athletes here, and let's say I had 5, let's go here by 5. I don't know the frequencies yet. It will be nice to have my table and my technology handy so that I can get that done, right? So I will say I have 5 values between 59.95 and 61.95. So I would sketch this like that. That will be my first bar. And then I would shade it in because it will be a solid color. And then for the next bracket, I am from 61.95, so say 62, to 63.95. So 62 to 63.95, I don't have anything. I just have 63.5, 63.5, 63.5. There we go. I only have 3. So my 3 would be, maybe that's a 4. So let's try a little closer to the middle. So that will be my next bracket. And then from 63.95 to 65.95, I would have, let's go back to blue, 64, 64, 64, 64, 64, 64, all of these guys. And that's it. 64.5, because the next one is 66 and it's out of that class. And these are 16 of them, if I count them. So then my rectangle would go up to 16. So try to pause the video and see if you can complete this. This is still incorrect. It has the number of athletes. After that, I will have to find the percent of athletes because they have asked me for a relative frequency histogram. If you have already done the project, you know that since the total is 100, 5 divided by 100 is 5%, 3 divided by 100 is 3%, 6 divided by 100 is 16%. So actually, it happens just because the total is 100, that the frequency and the relative frequency have identical values. Even if they didn't though, and let's say 5 as a frequency corresponded to 2%, then the histogram and the relative histogram would be identical to each other. So I would have calculated the frequencies, but then I would just replace them with the corresponding relative frequency. So let's pause here and let's try to see if you can generate this by hand. Then we will see how it can be done in Excel. So this is our relative frequency histogram. Remember that the frequencies and the relative frequencies were identical. I didn't have a very good numbering on my y-axis because the highest relative frequency was 39% and my axis only had room up to 35. So it could have been better if I had a better system of numbering my y-axis, but it's all fine. Let's see how it looks in Excel. So in Excel, if you go in the Unit 2 Excel file and in the tab Module 2.2, you have here in the beginning the heights in inches of 100 athletes. So you want to use that data set to generate a histogram. So when we are here, we want to highlight the 100 heights, 99, 100 right here, and we want to insert. And if we insert a histogram here, then Excel is going to make some decisions without us. And one of the decisions, for example, is to create a histogram that has 7 bins and to start at 60 instead of 59.95. Another problem here that occurs is interval notation in mathematics. So if you pay attention, the upper bound of every bin is equal to the lower bound of every other bin. And to avoid conflict, Excel uses interval notation. In interval notation, a bracket, a square bracket, denotes that the data value is equal to that value, and a parenthesis denotes that it is not equal to that value. So for example, from 62.2 to 64.4, we can equal to 64.4 because there is a square bracket here, but we cannot equal to 62.2. And then in the next bin, because we could equal 64.4 to the bin on the left, we cannot equal to 64.4 for the bin on the right. And then that will go to 66.6 inclusive. That means you could equal to 66.6. But then in the next bin, you cannot equal to 66.6. And because Excel is trying to include as many data values as possible, there is a little discrepancy here. The discrepancy being that in the first bin, Excel has both endpoints being included in the interval. So you could equal the left side, which is 60, but you could also equal the right side, which is 62.2. So that is something that unfortunately automatically gets done in Excel. Now, you can change this if you want, but again, it's never going to start at 59.95 unless you have advanced skills in Excel to change it. It won't do it, intuitively and automatically, and it will not be very easy for you to change. But the way to do that would be to click on one of the intervals here, one of the classes, right click on the horizontal axis and format the horizontal axis. And when you are here, you can select your bin width. You see here that it is 2.2, and we found it to be 1.7625, and we rounded it to a 2. So maybe we wanted to make it 1.8, and that would have been better. Let's say 1.8. Let's see what happens if we do that. So now it looks a little closer to our graph. And you could also just select the number of bins. So now that I did it 1.8, it actually did become 8 bins. You can also click on the number of bins and make them 8. Here 1.75. The 1.8 changed to 1.75 automatically because the number of bins were 8. That changed the graph. Again, doesn't look like the graph I had. Let's add data labels. And remember that the frequency and the relative frequency in this case are equal to each other because the total is 100. So this doesn't look like the one I wanted. Let's try again the bin width of 1.8 and see if that is better. Still, I don't have my 39% here. I don't have my 17%, but it does look much more similar to the one that I generated. Let's try again to format the axis. So if we had done number of bins equal to 8, and it would have defaulted to 1.75. Again, I don't get the values that I generated when I created my histogram. So again, it requires a little more digging into and more coding in Excel, but a better statistical software would have asked you, what do you want your minimum value to be, and what do you want, how many bins do you want, and then it would have done it automatically for you.